Measurement in one form or another is part of our daily lives. We have devices to measure hours and to wake us at a predetermined time. We measure our instant coffee and the water. A thermostat measures and controls temperature. Time, volume, temperature, all of these are measured as physical quantities, as are voltage, resistance, and inductance. Every physical quantity has magnitude. That is, we can measure it in relation to other quantities, and we call these measurements scalar quantities, as the attendant fills your tank. These are simple scalar quantities. Another scalar measurement is miles. But if you were instructed to drive 35 miles and then 60 miles, you'd want to know what directions, right? Scalar quantities aren't enough here. We need to add directional information. So if we say 35 miles north and then 60 miles west, we can figure out exactly where we're supposed to go. With the help of a map, we can see where we will be after 95 miles of directed travel. Quantities which combine both magnitude and direction are measured by a system called vectors. Now, if uncooperative fellows here pull in opposite directions with equal force, that crate won't budge an inch. Since the forces have both magnitude and direction, they are vector quantities. Vectors graphically show this as two equal and opposing lines from a common point. We can see how they more or less cancel each other out. If our stevedores decide to pull in a more general direction, but perhaps with different forces, what direction at any given time? In this case, we'll say their efforts are 90 degrees apart. If we graph their respective forces, we can complete the figure, and by drawing a diagonal line, we will have a resultant vector. The resultant vector is a line with both a length, or magnitude, and specific direction. We can tell exactly with how much force and in which direction will be the resultant from these two pulling forces. Map directions are a form of another distance in another direction. Our resultant can be mathematically figured if we want to know actual distance between these points. If we now drive 10 more miles southwest and 10 miles south, we have a trip containing 4 vectors. If drawn to scale, these directional arrows will produce a new resultant, which will indicate the true distance and direction from the starting point to our destination. Now, vectors can be combined in several mathematical ways to obtain the resulting magnitude and direction of 2 or more interacting forces. The direction is shown by the arrow, the magnitude by the length of the line. The resultant can be easily calculated by means of trigonometry, or the science of triangles. Now, if we move vector number 2 so that it joins the far end of vector number 1, we can create a triangle. If we square the two sides, add these squares, and then take the square root of the sum, we have 5. But we also need to know the direction of this 5-unit resultant force. We use the degrees of angle from the horizontal to identify direction. The Greek letter theta, a circle with a bar inside, is normally the symbol for an angular measurement. The horizontal or 0-degree line is always the reference vector. I'll repeat that. The horizontal or 0-degree line is always the reference vector. Forces 180 degrees from the reference oppose the reference, or are minus forces. If we consider current flow as a 0-degree force, there are 2 important forces which will have opposite or 180-degree directions. Can you think what they are? Well, one is opposing voltage, or counter EMF, even though our reversed battery is not an induced force. It is a form of counter EMF. The second force is pure resistance. Resistance opposes current degrees or phase angle, which, as we stated, is another way of showing direction. Now, a phase angle will not be greater than 180 degrees. A phase angle will not be greater than 180 degrees. A leading phase angle is any force which exists between 0 and 180 degrees. If the force direction or angle is greater than 180 degrees, we measure it backwards from 0 and consider it a negative quantity or a lagging force. Now, since resistance opposes current flow directly, and inductance and capacitance are opposite each other, 90 degrees from resistance, we can graph these forces in terms of degrees. When we illustrate these forces, we can see that resistance, R, pulls against voltage, as Ohm's law, of course, proves. But we can see that capacitance, which is related as X sub C and X sub L, will pull against each other. Now, if a circuit contains both, inductance and capacitance is opposed by a 6 ohm capacitive reactance. As opposed vectors 180 degrees apart, we find that 10 cancels out the 6, leaving only 4 ohms total reactance. Cancels may not be such a good word, but it will give you the idea in this case. 10 cancels out the 6, leaving only 4 ohms total reactance. There was more inductive reactance to start with. Therefore, only inductive reactance will remain to affect the current flow. A complete circuit also contains voltage and resistance. Here, 10 volts and 3 ohms. To find current flow, we must determine total circuit impedance. Again, vectors assist us. The resultant of our 3 ohm resistance and 4 ohm reactance form the two sides of this triangle. Now, if we add the squares of 3 and 4, we get 25, which is 5 squared. Knowing total circuit impedance, we can now easily find the current flow. As you see here, it will be 2 amps. 0 degrees. But as reactance increases in magnitude, the current direction, shown as the resultant of these two forces, will be drawn toward that force. As it does, the angle theta increases. In a purely capacitive circuit, the angle would be 90 degrees. The pure wattage, or real power, used by the circuit will form the reference vector. The reactive volt-amps, or VARs, forms a sector 80 degrees above or below the reference. The resultant vector is a graphic measurement of the total or apparent power being used within the system, and the phase angle of this vector indicates degrees of lead or lag of actual system current flow. Well, we were all supposed to have learned in school that if any two sides of a right triangle are known, the length of the third can be calculated. In any triangle with one 90-degree angle, the square of the length of the longest side, or better known as the hypotenuse, C, equals the sum of the square of the other two sides, A and B. To put it more simply, we say A squared plus B squared equals C squared. Now, in this right triangle, our A and B sides are 3 inches and 4 inches. If we multiply 3 times 3, which is A squared, we get 9. 4 times itself, or 4 squared, is 16. The sum of 9 plus 16 is 25. So we know that side C times itself equals 25. So what is the length of the hypotenuse C? Well, of course, it's 5. It's the square root of C. 5 times 5, or 5 squared, is 25. So our side is 5. Now, if we were to have a 90-degree reactance vector with magnitude of 3 and wattage vector of 4, we could easily compute the magnitude of the resultant, 5. Reversing the triangle somewhat does not change the magnitude, but now provides a resultant with the same starting point as the other two forces. The resultant force is a vector with a magnitude which represents the EMF. Now, if the base angle, theta, of any right triangle does not change, the sides will always be in proportion one to another. Here, at 37 degrees base angle, the base length divided by the long side, or known as the resultant, always equals 0.799. This proportion is called the cosine of 37 degrees. Each angle has a specific cosine. As this chart shows, the cosine can be used to find the true watts in a system if the total power and phase angle are known. In the example we just saw, we could measure total power, let's call it 5 kVA, and measure the phase angle of that power in relation to the applied EMF. Our scope would indicate a 37-degree phase angle. Checking 37 degrees on a cosine table shows 0.799. Now, if we multiply 5 kVA total power by 0.799, so if we multiply 5 kVA total power by 0.8, we see that the true power, or useful watts in this system, are 4 kVA, or 4 kilowatts. We also see that 20% of the power put into the circuit is wasted pushing reactive power, VARs. In our power vectors, then, a circuit with little reactive power will have a small angle and a cosine close to 1. The greater the VAR vector, the greater the angle, and the smaller will be the cosine number. We call this ratio number the power factor, a term used often in electric power industries. It is a ratio of watts to actual generated volt-amps. So a power factor of 0.985 means little reactive power, while a power factor of 0.423 would indicate that most of the generated energy is pushing reactive currents. The generated power in an electric system is a combination of watts and VARs. That's real volt-amps and reactive volt-amps. To find the wattage, we simply multiply the total power generated by the power of resistance and reactance. The angle, theta, of this resultant is called the phase angle, from which we determine power factor. Now, don't worry about having to do long, complicated trigonometric calculations to understand reactive power. If you grasp these basic concepts and terms, which we've just gone through, that's plenty for right now. To check yourself and find out just how well you have learned these concepts, answer the 10 questions on page 6 of your booklet. When you're ready, restart the machine again and we'll check your answer. Okay, let's go over the answers. Question 1 should read, a scalar quantity has magnitude, but not direction. Statement 2 reads, if several vector quantities combine, the net total is called the vector resultant. Hope you got that one right. It is an important concept. Number 3, the longest side of any right triangle is the hypotenuse. Now, if you said resultant, for purposes of this course, you can mark it correct. The hypotenuse and the resultant are pretty much the same. Next, vector direction is usually expressed in degrees of angle. For number 5, the vector sum, that is, the resultant of circuit reactance and resistance, is known as the impedance of the circuit, and of course it's abbreviated Z. Cosine of the phase angle is called the power factor. The cosine of the phase angle is called the power factor for number 6. Number 7 is false. counter EMF, and resistance both oppose current flow, so their force vectors would have the same direction, 180 degrees. Well, you don't really need a cosine table to answer number 8. Just remember that the smaller the angle, the closer the cosine is to the maximum, or 1. So the cosine of 16 degrees is closer to 1. Actually, number 9 is false. As phase angle, or power factor, increases, less energy is used as true power, more as VARs. Finally, number 10 is true. A basic understanding of the mathematics of triangles, called trigonometry, is helpful in understanding many science-related subjects, and vectors, of course, is one of these. Well, we've covered